Welcome to Climbing the Human Ladder, Step for Success in Science, the IISIAR podcast, where we explore inspiring scientific journeys and the untold stories shaping our research community. We are your hosts, so I'm Blandine Baffer from University of Virginia, USA, and
Paul Mike Jordan from the Friedrich Schiller University in Vienna, Germany.
And in each episode, we dive into a conversation with experts in innate immunity, sterile inflammation, autoimmunity, and the mechanisms that drive their resolution, bringing you insight, ideas, and inspiration you won't hear anywhere else. Whether you're listening with your morning coffee or while working at the lab bench, we hope this podcast gives you a fresh perspective on science and the people behind it. Today, we are delighted to welcome Charles Serhan. He is the Simon Gellman Professor of Anesthesia at Harvard Medical School and a Professor of Oral Medicine, Infection and Immunity at Harvard School of Dental Medicine, and the Director of the Center for Experimental Therapeutics and Reperfusion Injury at Brigham and Women's Hospital. So thank you for joining us and welcome to the podcast.
Okay. Hello.
Hey. So my first question is, could you briefly introduce yourself and your current role?
Okay. So hello, everyone. My name is Charles Serhan. And as she told you, I'm a professor at Harvard Medical School. I direct the Center of Experimental Therapeutics at Brigham and Women's Hospital. And we're very passionate in my lab about the mechanisms of resolution of inflammation and have focused on that for the past 2 decades or so.
More specifically, could you tell us a bit about your research and what question your lab is trying to answer?
I'm very interested in studying how the body resolves inflammatory challenge. And what we uncovered using self-limited models of acute inflammation that resolve on their own is that there is families of molecules that are made that regulate the innate immune system and direct the innate immune system to return back to homeostasis. And the first of these molecules we named the resolvins. And the resolvins limit neutrophilic infiltration. So there's less collateral tissue damage, and they lower the magnitude and the amplitude of the acute inflammatory response. They also direct macrophages and help them change their phenotype to a pro-resolving M2-like phenotype, and then stimulate those cells to take up debris and apoptotic neutrophils. So our studies have focused on the structural elucidation of those molecules, on identification of their cell surface receptors, which are GPCRs, and have determined the complete biosynthesis and stereochemistry of these molecules by taking a total organic synthesis approach. And then we learned that there is a second family of molecules we call protectins, of which neuroprotectin D1 belongs. And when macrophages come to the site of inflammation, they make their own mediators, which we named the macrophage mediators of resolution, or the merisins. So there are a whole superfamily of molecules that are produced at the site of inflammation to take us back to resolution. And that's what we've been busy studying. And now there's many groups around the world studying these molecules. They're all commercially available. And just this morning in PubMed, there are 2,060 papers on just the resolvins alone, confirming their potent actions and expanding our knowledge of their roles in regulating inflammation and their signaling.
Thank you so much. So, what first drew you to the field of immunology or inflammation?
When I was in school at NYU Medical, I was very lucky. And someone in the dean's office noticed that I was interested in chemistry. And I had done chemistry research as an undergraduate, and I was a biochemistry major. So she said, I think you should go up and talk to Dr. Heidelberger. He's looking for someone to help him. And here I am, this young person, and I met Michael Heidelberger. He was 91 years old at that time. He was a organic chemist by training, but he was considered the father of immunochemistry. And I worked side by side with him. He was the first president of the American Association of Immunologists. And his student was Cabot, and Cabot determined the structure of IG. And Cabot's student, so Heidelberger's scientific grandson, was Benasarev. And Benasarev got the Nobel Prize in Physiology or Medicine in the early 1980s. So I was introduced to how the body reacts to microbes by Dr. Heidelberg, and that he told me when I was a student there that I should go talk to another professor because he said, Charlie, I'm a little bit too old to have a student now. So, okay. So he sent me to see Gerald Weissman, who was well known for studying inflammation. He was an immunologist and rheumatologist. And that opened up the whole world to me of neutrophil and leukocyte biology. So I learned that all from Jerry. And then I had an opportunity to go to the marine biological laboratories at Woods Hole. Jerry had sent me there. And when I was there, I met Bengt Samuelson. And Samuelson heard me present our summer research project that year, and we had gotten the MBL award for the research that summer, which was quite fun. Samuelson told me, when you finish, there'll be a place for you in Stockholm. And I was really, I was like, oh my God, I never thought about it, finishing school, because I'm from New York City and going to Stockholm. It just was not part of my plan. But I thought it was a really good opportunity. And then when I went there and, really took a deep dive into arachidonic acid biochemistry and chemistry, I did some of the early work on leukotriene B4 in humans with human neutrophils. But then when I was there, Samuelson got his Nobel Prize in physiology or medicine, and I got a chance to go to the Nobel Fest. And I was really fortunate because Samuelson cited two of my thesis publications in his Nobel lecture. Wow. So all those things made me very excited about studying the innate immune response. And as you know, any immunologist probably 20, 30 years ago focused more on the adaptive immune response and left the innate cells to hematology and to other fields. So I remained committed to neutrophils. And when I came to Boston, I was again lucky, and I was really interested in vascular endothelial cells. And I got a chance to work with the people who isolated endothelial cells for the first time. And I've kept that interest of how neutrophils talk to vascular endothelial cells um, right up until now.
Thank you, Charles. It is a great scientific journey. And was there also a pivotal moment that shaped your scientific path, planned or also unexpected?
Well, Paul, I was really lucky. I always knew since I was very young that I loved chemistry. I just thought there was something really magical about chemistry. Frankly, I did not plan my career steps. I would have to say all along the way, I kept my passion towards the science, and everything else was serendipitous.
And was there a personal motivation that influenced your work or also your career?
Well, that's a critical question. I I I should tell you and the audience that I think it's very important to have scientific heroes, you know? And not just look at their publications, but actually study their research trajectory. And, you know, um, in many respects, Samuelson was one of my scientific heroes. E.J. Corey was another in chemistry. And having a chance to meet them all was really inspiring. But in terms of my own research interests, I knew I wanted to work on an important problem, meaning one that affects many, many people. And it seemed to me, even as a student, that uncontrolled inflammation uh, affected many, many disease pathologies. And I had this impression early on that our treatments were not adequate and that we could do better. And that is really what brought me on to the journey of finding endogenous local mediators that we could use as therapeutic templates to make more precision directed mechanisms because, the way inflammation is treated still today is by blocking or antagonizing the chemical signals that are produced, which is the language of inflammation and resolution. But what we learned from the Resolvins early on is that we have to learn to stimulate the body's own resolution mechanisms. And this was a much safer and well tolerated way. So that's a journey that we are on together.
So let's move to another topic. So could you highlight a project or discovery you're particularly proud of?
I'm a father of three. Um, they're all grown. And, but that's a hard one because I have to say, I love them all. That's like saying, which is your favorite? They're all my favorites. I'm really lucky that each of the contributions we've made have continued in the hands of others and in companies moving forward. So I'm very proud of that. And I'm very proud of all those who've come to my lab and who've trained and have their own labs and their own exciting research programs. And that's made it all really fun and worthwhile.
And are there technological developments that have recently transformed your research?
Yeah, I think the most important development in my time, when I started in the field of lipid mediators, as I said, I worked on the leukotrienes and prostaglandins. One of the prostaglandin papers was one of my first. Um, we use gas chromatography and mass spectrometry. And when I came to Boston, when I was recruited here, the first LCMS MSs were appearing, and I was really excited about that. So I got in touch with my friend, Pierre Bourgeat, and he was a professor in Canada. And he had also been a postdoc with Samuelson just before me. And he invited me up to Canada, and they had the first LC-MS-MS, and I was able to get LC-MS-MS spectra of lipoxygenase pathway products. I was really excited about that. And now, today in my lab, I have two LC-MS-MSs, and the advantages of that is that we can do multi-reaction monitoring and monitor 60, 70 different lipid mediators in one run, which is a big advance. In the past, we could only do one molecule at a time and make a methyl ester and an OTMS derivative, and that was really painful work. So that's been a really big event, and people all around the world now use the LC-MS-MS methods and are doing profiling and profiling in human health and disease.
So, my next question is, how do you see the connection between basic research and real world applications?
I see them as the same. And you might say, well, why? How could you say that? Well, if you look at, let's say, Louis Pasteur. Louis Pasteur, he worked on problems that were very big, but very basic, and it changed the world. Uh, I like to think that we're doing that. I think controlling inflammation is a really important part of health and disease, and if we can do it better, people will live longer, have less pain, and, so I think a really good basic research program is actually pitched towards solving a real world problem.
Coming to the impact of science for the society, what do you see as the societal research impact of your research?
Well, that's a tough one. I think we've had a good impact within the scientific community. I was just happy to see that my H index hit 200 last week.
Congratulations.
Thank you, Paul. It at least says that others are using our work to move forward. I just recently was contacted by um, a fellow from the Netherlands, and he wants to have a podcast devoted to SPMs because he thinks that the resolution of inflammation needs a forum outside of the basic science and that it's of general interest. So I was surprised to hear that. I said, sure, I'd be happy to help with that. So I think in terms of athletes, and we all, during our periods of good health, we still at times feel pain and have bouts of uncontrolled inflammation. So I do think that there is a social impact to this work, particularly in the area of neurodegenerative diseases. As you know, neural inflammation in excess, helps to bring about neurodegeneration and aging. So I think if we have more tools to understand how to increase the production of mediators that can control excessive inflammation, you'll have a great social impact.
Absolutely agree here. And we know that you are engaging in scientific outreach. Is there a specific moment you want to share with us?
I frankly still get nervous when I have to go out and give a talk. But just this past weekend, the American Association of Immunology had the annual meeting in Boston. And for the very first time, they invited us for resolution of inflammation major symposium. So for me to open up to give that first presentation to very knowledgeable colleagues, but hadn't heard about resolution or the resolvins, it was the very first time. That was a big deal for me. And then Gabby Fredman gave a great talk, and Patricia Symes gave new results. And Dr. Sharma, who is a vascular surgeon from Florida, he gave wonderful data on aortic aneurysms. And all in all, people were very excited. They walked away like they had learned something new. And that was a scientific moment.
It's great to hear. And how important is it for scientists to interact with the broader public?
Well, I think that's very important. I'm glad you bring that up because right now in the US, I think we're suffering because there's a disconnect um, of the important work that's going on from the NIH and our politicians. Things are a bit delayed right now. And so I do think it's very important for scientists, especially biomedical scientists, to reach out to those that are interested, but also those that are playing a role in local politics. And eventually, like I just wrote a short email to our congresswoman to see if she could help to leverage and get the NIH to be able to release funds because unfortunately, our business is very expensive. And even though we serve humanity's greater good, it is an expensive ordeal. And to be engaged in true research. Um, so we have to be mindful of that. and help to persuade those in government and in politics that this is an important endeavor for humanity.
The next topic, building a scientific career. So, what strategies help you navigate difficult moments in your journey?
Okay, this is a very important question, and I'm going to give you an answer that is going to surprise you. So, when I was a kid and I was with Dr. Heidelberger, I said, what's the most important things um, that I can do to become a good scientist?" And I remember I was in my early 20s and he was 91. And he won the Lasker Award twice in his career. Twice. One time when I was there. I couldn't believe that. Okay, so he told me, and I tell this now to you, that, Charlie, it's important that you work on projects that you are passionate about, because if you are passionate about them, that will carry you through the hard times. So that's number one. And number two, this one is even better. He said, you have to write everything down. He said, carry a small notebook, doesn't have to be a big notebook, put it in your lab coat, and as you make observations, write them down and review them, because there will be your discoveries. And if you don't quickly write your observations down, you won't be able to remember them all and string them together. So yes, I still do that today. I still have my little books that I write in.
Okay, interesting. And were there any decision you initially adopted that turned out to be the right choice?
I think even though my friends and colleagues and my parents thought I was crazy going to Stockholm at the time, that was a good choice, especially when Samuelson got his Nobel. I mean, that was so much fun and put such a big spotlight on the field. I think the second was making a commitment to do the structural elucidation of the specialized pro-resolving mediators and then making them all commercially available, because that's made the field really expand. So I think those were all. Time will tell.
How do you evaluate and size new opportunities while managing ongoing commitments?
I always am committed to follow through on my specific aims. But to follow through to completion sometimes takes many years to do. And of course, during that time, other opportunities come up. But I have to say that I maintain focus, uh, and I like to bring new things into my field and interest, but I won't disengage from my objectives to go into something else. So it's always good if someone has a new microscope, we'll get that microscope, but we'll point it at resolution of inflammation.
So next, let's focus on the leadership and research culture. So how do you build and lead a successful research group?
Ooh, that's a hard one. I don't know. I think I have been very fortunate to have a lot of people come to work with me. I've been program director of program projects, and actually 3 of them supported by NIH, which are multidisciplinary research teams going from chemistry to pulmonary medicine, oral medicine, and dentistry. Um, I also was a program director for a NIH-supported P50 grant, and that also had big multidisciplinary teams. I think if everyone's on the same mission, if the mission is clear, people just work together to move the mission forward. I don't really think it takes any managing at all. It just takes I guess the key thing is to always have good people coming and help and making an effort to have good people come.
Okay. And what helps maintain a positive and collaborative lab environment?
I always love to collaborate with people because they bring a different perspective, they bring different systems, and it's a shared learning. That's the way I look at it. Even when I have students, if we take on a new um, directive, I feel we're learning together. I learn from them, their point of view, they learn from me. And so it's all about being open to learning, which is our business. That's not so hard.
Yeah. So, what qualities do you value most when mentoring students and trainees?
Honesty. I I like when people are direct and frank with me. I am sometimes too direct and too frank with people. You you can ask Paul because Paul's been here. What do you think, Paul?
We discussed a lot, Charlie.
um, I found that my mentors always challenged me, and so I have found subtle ways to, because things change with time, to challenge people who work with me in a good way, in a way to improve the field.
Absolutely agree here, Charlie. And it was really a challenging time, but it was a great time in your lab. And now we are coming to the section skills and professional growth. One question here is what non-scientific skills have been most important in your career?
I think the most important aspect for any person um, is to have a strong faith. And this helps to drive um, the scientific questions. And it's very important for me. I still pray for my grants.
Okay, yes. Going further, another question is what skills do you think are often overlooked but essential for young scientists?
Yes, I think, and I wish in my own development, the the importance of communication, both in oral presentation, in making powerful illustrations, and in writing. Writing impactful papers that go across the field. This takes some special training and studying to do that. So I would say the most important skill is communication because you have to be able to tell people what you do and you have to be able to communicate to other scientists, but also non scientists. Do you agree?
Definitely.
Absolutely. Yes.
So I do believe this next part will be especially exciting for the next generation of scientists who are listening to us. So, what advice would you give to someone just starting in this field?
I have to go back and say that you have to have scientific heroes if you're just starting out, and you have to study not just their publications, but their trajectory, how they put it all together, and how they maintain focus. And then, as we discussed earlier, that they have to find what they're most passionate about to put their time and effort in on.
What challenge and opportunities do you see for the next generation of scientists?
I think what we're seeing now, the challenges are how to sustain momentum in the medical sciences and keep in concert with political agendas. Again, because this is tied to the economics and of our endeavor, and things have changed a great deal. At one time, I would say big pharmaceutical companies helped to invest in basic research and then work together with scientists and academia to help to bring uh, new therapeutics, new devices into use. But this is happening much less today. And and so I think for young people to be innovative is of course essential in their work, but then also to be entrepreneurial is important. How can I fund those ideas? This is what you need to ask yourself. How am I going to bring this to people? Um, and what do I have to do to get there? So, entrepreneurialism today is much more important than at the time when I was beginning my research.
Coming to our last question now. Is there a memor memorable moment from your career that you like to share with us?
A memorable moment? Well, this is a good one. I like this one. I have two. So, as I said, I was at the Marine Biological Laboratories, and we worked under pressure there. It's time pressure, and there was a problem that we couldn't challenge. And we worked very closely with Jerry Weissman, he was the professor at the time, and a colleague of mine uh, who is now one of the deans here at Harvard, but we were just students then. And and we couldn't figure out this problem. So I left the lab. I went out. I took a long walk, tried to relax. I came back to the lab and I had the solution. And I immediately did this. It was using a dual photon spectrophotometer at the time. And my boss came running in, saw the results, and he said, "You are a clinch hitter. You're a clinch hitter." So do you know what a clinch hitter is in baseball?
No.
Well, I like baseball, so I'll tell you. The clinch hitter is when the team is down and they send in the guy at the bat who's going to hit a home run. He's called the clinch hitter. So even when things are down, he hits a home run. And so that was a very positive experience for me, and I was very happy about that. When I was at the Karolinska, I was troubled with this HPLC tracing that I was getting, and so there was a gym across the street, and I used to belong to the gym, so I went to the gym and I was working out, and I was sitting there, and this was, lifting weights. We like to do that at that time, and it came to me. Wha it just the answer was right there. As soon as I relaxed, I ran back to the lab. I got a full UV spectra, and it was the first tetraene spectra. It was lipoxin A4. And today there are thousands of publications on lipoxin A4, and I'm really happy about that. So that was memorable for me. So the take-home message for those who are listening is that if you're troubled with a problem, if you can't solve it, go out and relax. Whatever you need to do. I needed to walk, I needed to go to the gym, and then your mind, I believe very much in what people used to call the cybernetic theory of the mind, which your mind will get you the answer when it's not. You put the information in, and then the right answer will come. And I've always seen that to be true.
What a closing remark. Thank you. That's a wrap for today's episode of Climbing the Immune Ladder, Steps for Success in Science, IISIAR podcast. A huge thank you to you, Charles Serhan, for sharing your insights, experience, and perspectives with us today. We hope you found this conversation as inspiring and fruit-provoking as we did. If you enjoyed this episode, don't forget to tune in for the next one and share it with anyone who might benefit from it. You can also follow us on our webpage to stay updated on future episodes and the latest news in innate immunity. Thank you for listening. And remember, persistence and asking the right questions are what drive science, and maybe even your own journey. Until next time, stay curious.